All right, hey everyone, and welcome back to our linear algebra lectures. This is starting off chapter 4, and all of chapter 4 is devoted to this thing called an eigenvalue or eigenvectors. Um, it's like, why, like, what is that? We've never heard of it. And why are they so important? So I want to point out a very interesting phenomenon. Oh, by the way, if you went and read section 3.7, you will have seen that by when you take a matrix and apply it a bunch of times, sometimes the process will stabilize, and you'll end up in like uh, a loop where applying the matrix to a vector over and over doesn't really change the value of that vector, or maybe it like all it does is eventually scale that vector over and over. Okay, so let me just point out an example of that. So let's take a look at this matrix: 0, 4, 3, 1/2, 0, 0, 0, 1/4, 0. And we're going to multiply it by this vector: 36, 12, 2. Okay, when you do, you get, you can just check my matrix multiplication on this one. You get 54, 18, 3. But that is exactly 3/2 of the original vector that you started with. The output was a multiple of the input. Okay, that seems abnormal because very rarely has that happened over the entire course of our class. Like normally you just put in a vector and you get out some other random vector. Why should the output be related to the input? Is that something special about the matrix? As it turns out, no. It's something special about the vector that we put in. It's the matrix and the vector that we chose. Yeah, it was carefully fine-tuned so that would happen. And so we come to so that sparks a curiosity. It's like, okay, wait, can we always do that? That's called the eigenvalue problem. So let me state the problem. It's given a square matrix A, can you always find a non-zero vector x such that ax is equal to lambda x for some scalar lambda? Now it's important that x is non-zero because like, okay, wait, that's always true if it's the zero vector. Take a matrix, multiply by the zero vector. Yes, you will get a multiple of the zero vector, namely every multiple of the zero vector. That's dumb. We don't want that case. We want something weird like this, where it's like not many zeros in sight, and yet we just took a vector, multiplied by the matrix, and we got out a multiple of the vector that we put in. When does that happen, and how often does that happen? Does it always happen? The answer is no. We'll see an example of that. Okay. So let me give you a definition. This definition is going to actually sound very similar to the eigenvalue problem because it's the definition of an eigenvalue. Okay, so let A be a square matrix. A scalar lambda is an eigenvalue of A if there is a non-zero vector x such that ax is equal to lambda x, this equation that we just were asking about. And we call that vector an eigenvector corresponding to lambda. Just some etymology stuff. It's eigen, E-I-G-E-N. That's from the German word to own or something like that. So it's not like we don't capitalize it. It's not like named after a person. It's like special vector. Think of it that way. But it's pronounced like gun from your eye, like eye gun. Okay. Okay. Eigenvector, eigenvalue. Yeah. Okay. Anyway, just in case you're like, is that Egan? Egan? No, eigenvalue, eigenvector. Okay. Anyway, just fun. Okay. Okay. So let's just test the definition on a vector and a matrix. Show that 1, 1 is an eigenvector of A, and find the corresponding eigenvalue. Don't find eigenvector. What? Yeah. Find the corresponding eigenvalue. So, well, 3, 1, 1, 3 times 1, 1. This is ax. This should be equal to lambda x. By the way, another etymology thing. This is kind of cool. The like, what is this that I keep drawing? It's like an upside down Y or something like that. Let me do this in a different color. This is the Greek letter lambda. And the B is silent. Lambda. And it is the same. It does the same thing in Greek as the letter L in English. Okay. And so yeah. So okay. But the reason for that is because once upon a time, a long time ago, these eigenvalues were called latent values. They were values that stayed after doing some process, right? Well, we know that as applying a matrix, right? So anyway, so I put a hook on the top. You can do it like this. I warn you, if your second line sticks through, I don't know if that's an X or a lambda, and I can't promise that I'll be able to tell what you mean. Because like, look, lambda X. So I will do my best to keep my handwriting clean, even though we're writing Greek. But I ask the same of you on like homework and stuff. Okay, great. Let's do it. So what is this matrix product? Well, that's pretty easy. It's 4, 4, which is equal to 4 times 1, 1. There's your lambda. There's your x. Okay. So lambda equals 4 is the answer. Lambda equals 4. Okay, now let's go. So given an eigenvector, we were able to compute the eigenvalue. Now, we want to show that 5 is an eigenvalue of this matrix A, 1, 2, 4, 3. That's harder. Okay, let's think about this. To be an eigenvalue, you need to have that ax for some x is equal to now 5x. 5 because they told us what the eigenvalue is, right? Well, subtract from both sides. Ax minus 5x equals 0. 0 vector. Factor in x because we can like factor, left distribute, whatever. This is going to become a minus 5 I2. I2 being the 2 by 2 identity matrix. It's going to be this is a matrix, the difference of two 2 by 2 matrices. That thing times x is apparently equal to 0. Okay, we can actually compute this. When we do 1, 2, 4, 3 minus minus 5 times 1, 0, 0, 1. 5 times that matrix is just put 5s on the diagonal. The scalar matrix, which scales by 5, times x, which is 1 minus 5 is negative 4. 2, 4, and then 3 minus 5 is negative 2. That's a suspicious matrix. So now we want this to be equal to 0, but notice this is the matrix form of an equation. This is matrix form for a homogeneous system of linear equations. In other words, we could solve this by row reducing this matrix. Negative 4, 2, 0 for negative 2, 0. Oops. When you do, you have, we'll put it in reduced row echelon form. It reduces to, you can do this one in your head, right? Just add the two rows together and then divide the top row by negative 4. So 1, 0, negative 1/2, 0, 0, 0. In other words, so if x is like x1, x2, then this is telling us that x1, so x2 is a free variable, and x1 equals 1/2 x2. In other words, so the solutions are of the form x equals x2 times 1/2 1. In other words, or t. I guess we should probably, parameterize our solution set. So let t equal x2 or whatever, right? Do a parameterization. So non-zero multiples of this vector apparently are eigenvectors. That's what we were trying to find all eigenvectors corresponding to the eigenvalue lambda equals 5. Well, apparently every multiple of 1/2 1, or maybe let's, you could also do t times 1, 2 if you don't like fractions. After all, 1, 2, any multiple of 1, 2 is also a multiple of 1/2 1, right? Just, well, anyway. Wait, so there are infinitely many eigenvectors. We should check this. So let's do these two. 1/2 1. Take this thing, multiply 1, 2, 4, 3. And what do you get? Well, okay, 1/2. You get 5 halves and 5, which is precisely 5 times 1/2 1. Check that with 1, 2. And what do you get? Well, you get 5, 10, which is precisely 5 times 1, 2. Every time. Yeah, so any vector of this form is going to have this property. They're all eigenvectors, but they're all eigenvectors corresponding to the same eigenvalue. Now, that seems like infinitely many eigenvectors for one eigenvalue. That seems strange. We give a definition to the set of all, well, let me just tell you what it is. We call it an eigenspace. So if A is an m by n matrix and lambda is an eigenvalue, then the collection of all eigenvectors which correspond to that eigenvalue lambda, taken along with the zero vector, those all make up the eigenspace of lambda. And we just write E lambda for it. So like E6, or whatever. Now, the reason we have to include the zero vector here is because, remember, the zero vector is not an eigenvector for any eigenvalue because it's the one that we wanted to throw away. An eigenvector is by definition a non-zero vector satisfying that ax equals lambda x thing. But we need the zero vector in order to create a subspace. And so, but fortunately, since the zero vector is a multiple of any eigenvector you can come up with, just go and multiply that thing by 0. You get a vector which satisfies x equals lambda x. That's fine. It's just that it's not an that vector is not an eigenvector, but we include it so that we can make an honest subspace. And sure enough, these things make up an honest subspace every time. So let's go and compute E6 for this 3 by 3 matrix. Make sure we have enough space. Yep. So computing E6, that's in other words, what we have to do is they're claiming that 6 is an eigenvalue of this matrix A. We're going to believe them for now. The book actually goes and verifies this. You can too if you want. But remember, E6 is just the null space. I guess we didn't say this specifically in the previous problem, but it is true. E6 is the null space. It is null. It's the null space of A minus 6I. That is precisely what we computed up here. We found the solutions to the homogeneous system defined by this matrix or whatever, right? And so for those of you who are wondering, who cares about null space, nullity? Yeah, it turns out null space has a very natural context as the dimension of an eigenspace for whatever matrix. And we'll see later on in section 4.3, I think, that you can have we can have several different eigenspaces, all of different dimensions, all kinds of interesting phenomena. So so this is application of the null space. So remember, we're going to have to solve a homogeneous system of equations. So let's do it. A minus 6I. So A minus 6I is, I'm not going to go and write out all of the matrix subtraction. I'm going to say it verbally. I'm going to subtract 6 from each of these diagonal components and leave the rest the same. You can verify that's exactly what we're doing with A minus 6I. But it gives this matrix 1, 1, negative 2, negative 3, negative 3, 6, 2, 2, negative 4. If you augment that with the zero matrix and row reduce, you're going to end up with row reduce. I'll just row reduce this thing. Because remember, row reduction is not going to change the columns in the augmented part of the homogeneous system. So row reduce, and you get first row. Okay, notice. Okay, I'll just say it. The second row is just negative 3 times the first row, and the third row is just 2 times the first row. So 1, 1, negative 2. You don't even have to check, you just have to squint at it. Both of those rows are gone with 2 row reduction steps. Yeah, okay, great. So we want to find what the solutions are. Notice x2 and x3 are free. We'll put s equals x2, I guess, and t equals x3. And now now we have x1 equals negative x2 plus 2x3. And so the x vector, the solution to whatever the homogeneous system is precisely negative x2 plus 2x3, x2, x3, which in terms of s and t is just s times the vector negative 1, 1, 0, plus t times the vector 2, 0, 1. This is a two-dimensional subspace. And in fact, E6 is none other than the span of these vectors. -1, 1, 0, and 2, 0, 1. A two-dimensional vector space, subspace. Cool. Okay, I want to do some geometry for a moment, because like linear transformations and matrix multiplication and stuff like that is geometric, and it's easiest to see the geometry happening in R2. So what is an eigenvector geometrically and in R2? Remember, ax equals lambda x means that the output after multiplying your vector by a, or multiplying a by your vector, gives you a new vector, which is just a scaled version of the original one, but a scaled version of a vector is parallel, right? So remember, we had this matrix 3, 1, 1, 3. We took the red vector 1, 1, multiplied it, we got 4, 4, which is 4 times as long, but parallel. If you look at these, like for example, the standard unit vectors, and their negatives I've done. The red ones, these brown ones or whatever, get kind of like squashed towards the red one and away from the blue thing. But if you go exactly at -45 degrees, or I guess 135 degrees or whatever, this blue one is also behaving like an eigenvector. Okay, and yeah, it's kind of like any other vector gets like pulled this way, you know. Oops. If you have some vector, it gets pulled this way. This kind of thing. Okay, anyway. And then if you're on the other side, the effect is to get like, pulled towards this almost attracting line, and pushed away from this repulsive or repelling line. It's very strange behavior. And so we would like to know, what is this? It looks like it's -45 or like 45 degrees, whatever. What is this? 135 degrees around, starting from the positive x-axis. That's what it looks like. Do we know that for sure? Or how can we prove it? And so that's the last question that we want to address, which we're going to have to do only for 2x2 matrices. Later on, we'll come up with a strategy using the determinant of a matrix, which we've alluded to, but we haven't actually said, and we'll define it in the next video. But we do know the determinant for 2x2 matrices. It's AD minus BC. Remember that? So the question is, how can you go and find all the eigenvalues? Well, an eigenvalue is a number lambda such that this a minus lambda I has a non-trivial null space. To have a non-trivial null space is the same as not being invertible. That's like triple negative or something like that. To have to be invertible, from the fundamental theorem of invertible matrices, a matrix is invertible if it has a trivial null space. So if you don't have a trivial null space, then you're not invertible. But if you're not, we have a characterization for when a matrix is not invertible, 2x2. It's when the determinant is equal to 0. In that case, that matrix is not invertible. So we are looking for matrices, for values lambda, for which the determinant of a minus lambda I is precisely 0. Let's do it for a. Okay, we can do it. It's not bad. A minus lambda I. We want the determinant of this to be equal to 0. Well, that's the determinant of a minus lambda I is the thing that you get when you subtract lambda from the main diagonals of a. So 3 minus lambda, 1, 1, 3 minus lambda. Now remember, the determinant is AD minus BC. Don't get too attached to that. We're going to learn a better version. It's just that this is a quick shortcut, and it's sort of a backdoor to determinants. So we don't have to go and learn the whole theory of determinants before doing an eigenvalue computation, that would be gnarly and not the right order to learn it in. You're going to have to take my word for it for now. So this is going to be, well, AD, that's the product of the main diagonals. So 3 minus lambda times 3 minus lambda minus BC. But BC is 1 times 1, which is 1. Remember your polynomial multiplication. This is 9 minus 6 lambda plus lambda squared minus 1, which is lambda squared minus 6 lambda plus 8, which factors as lambda minus 4, lambda minus 2. A polynomial, quadratic, we want to set it equal to 0? Oh my god. Lambda equal 4 and 2. Okay, great. We already did this one. So here's the other one. Lambda equals 2. When lambda equals 2, okay, so now we want to go and find, does it say find all the eigenspaces? All eigenvalues and eigenspaces. Great. We already found the eigenspaces for the first one. So E4, let me just remind you, we didn't have the language for it, but let me just remind you, it was the span of 1, 1. Great. We already did that computation. And by the way, E2 is going to be the same. So A minus 2I is it's a great matrix, 1, 1, 1, 1, because you just do this but plug in lambda equals 2. When you row reduce and do the augment and stuff like that, you end up with x1 equals negative x2, where x2 is the free variable. So E2 is going to be the span of negative 1, 1. Oops. Okay, and that's okay. I'm omitting details, but it's because that computation is exactly the same as the first example that we did. I'll go and like figure out all the eigenvectors for one particular eigenvalue, namely lambda equals 2. Also, back to the geometry. Notice this one's only getting doubled in terms of length, whereas this one's getting quadrupled. Corresponds to two different eigenvalues. And the eigenspaces are the lines spanned by those vectors, literally all the way out in either direction. So there we go. This is it for the 2 eigenspaces and 2 eigenvalues. Okay, if this sounds like a fun topic, let me tell you, it gets better, like significantly better as we go on. We're going to start to talk about more and more like broader eigenspaces and things like that. So, but anyway, that's all for this video, and I guess I'll see you guys in the next one.